Today we are going to talk about how to algebraically solve the system of linear differential equations. Basically, our problem is as follows. Given an equation x prime equals ax, how do we solve this equation and get the solution x? For simplicity, we are going to assume our x consists of two functions of t, x1 of t and x2 of t, and our A is a 2x2 matrix, which is given by the problem, and we are assuming our A is a real matrix. Here is our strategy. Depending on whether our A is diagonalizable or not, we will go to case 1 or case 2. In case 1, depending on whether our eigenvalues, lambdas, are real or complex valued, we will go to case A or case B. In each case, we will have an explicit formula for our solution x. After seeing our recipe, let's look at one example to perform our strategy. Here is example 1. Given the system of equations x1 prime equals 2x1 plus 3x2, x2 prime equals 12x1 plus 2x2, and given initial conditions x1 of 0 equals 1, x2 of 0 equals 3, our task is to solve this system of equations and get the solutions x1 of t and x2 of t. Firstly, we have to convert this system of equations to a matrix equation because our recipe is assuming we have a matrix equation. If you know how to multiply two matrices, you can verify that the first row, 2, 3, multiplied with the first column, x1, x2, will give you the correct right-hand side, 2x1 plus 3x2. And similarly, the second row, 12, 2, multiplied with the first column, x1, x2, will give you the correct second right-hand side, 12x1 plus 2x2. This matrix equation is better because this matches the form x prime equals ax, given in our recipe, where A is equal to 2, 3, 12, 2, which is a 2x2 matrix. Let's try to recall what is our recipe again. If you look at the recipe, you can see that depending on whether our lambdas are real or complex valued, we will have different cases. And also in our formula, we have our v1 and v2. This means that in order to apply our strategy, we have to know what are our lambda 1, lambda 2, v1, and v2. To calculate lambda and v, we will use two equations, determinant a minus lambda I equals 0 and a minus lambda I v equals 0. This lambda is called the eigenvalue of A, and this v is called the eigenvector of A. This eigenvalue and eigenvector are actually determined by the matrix A. The process to get our eigenvalues and eigenvectors, lambda 1 v1 and lambda 2 v2, is a bit tedious, so let me skip this step first and I will go back to explain this step later. Let's assume somehow from the matrix A, we know our lambda 1 equals 8, v1 equals 1, 2, lambda 2 equals negative 4, and v2 equals 1, negative 2. Let's see how do we apply the formula to this case based on this information. Firstly, we got our v1 and v2, which are two different eigenvectors here. So that means we should go to case 1. Secondly, we got our lambda 1 is equal to 8 and lambda 2 is equal to negative 4, which are real numbers. That means we should go to case A. This means that we are going to apply the first formula, x equals c1 exponential lambda 1t v1 plus c2 exponential lambda 2t v2. So let's record this formula here and see how do we apply this formula to this case. Since we know our lambda 1, v1, lambda 2, and v2, that means we can replace lambda 1, v1, lambda 2, v2 in our formula by the corresponding numbers or vectors. After this replacement, let's try to apply the initial conditions given in the question. So let's replace t by 0. For the right-hand side, we have exponential 8t and exponential negative 4t. They will become 1 when t equals 0 because exponential 0 equals 1. For the left-hand side, when t equals 0, x becomes x of 0. And from the question, we know that x1 of 0 equals 1, x2 of 0 equals 3, which means x of 0 is equal to 1, 3 vector. In order to solve this matrix equation, let's look at different components. The first component will give us 1 is equal to c1 times 1 plus c2 times 1. The second component will give us 3 is equal to c1 times 2 plus c2 times negative 2. So we got a system of equations for c1 and c2. We can either use substitution or subtraction method to solve this system of equations, and finally we should get c1 is equal to 5 over 4 and c2 is equal to negative 1/4. After getting our c1 and c2, we should go back to our formula for x and replace c1 and c2 by the corresponding numbers. After the replacement, we get an expression for our x. There's another way to rewrite the right-hand side. If we look at the first component of the right-hand side, that will be 5 over 4 exponential 8t times 1 minus 1/4 exponential negative 4t times 1. So we can collect these two components. And similarly, if we look at the second components, that will be 5 over 4 exponential 8t times 2 minus 1/4 exponential negative 4t times negative 2. After algebra, we will get the following equation. Recall that our definition of x is actually a column vector x1, x2, so we can replace x by x1, x2, and this is our final answer because we know that our x1 should be equal to 5 over 4 exponential 8t minus 1/4 exponential negative 4t, and similarly our x2 is equal to 5 over 2 exponential 8t plus 1/2 exponential negative 4t. As an explanation of the previous skipped step, let me try to tell you how to calculate the eigenvalues and eigenvectors of a 2x2 matrix A. In order to calculate the eigenvalue lambda and eigenvector V, we have to make use of two equations. The first is determinant A minus lambda I equals 0, and the second is A minus lambda I V equals 0. From the first equation, we can replace A by the given matrix 2, 3, 12, 2, and replace I by the identity matrix 1, 0, 0, 1. Next, we perform the matrix algebra to combine the two matrices by subtraction, so we will end up with 2 minus lambda, 3, 12, 2 minus lambda. There's actually a simpler way to write the determinant, which is to replace the bracket by the vertical bars. Using the definition of the determinant of a 2x2 matrix, we get 2 minus lambda times 2 minus lambda minus 3 times 12 equals 0. Next, we apply the distribution rule to simplify this quadratic equation, and we will get lambda squared minus 4 lambda minus 32 equals 0. Finally, we can either use the formula for the quadratic equation or use the factoring method to get our final answer for lambda, which is 8 or negative 4. Let's record our final answer for lambda above and try to make use of the second equation, a minus lambda iv equals 0, to solve for the eigenvector v. Firstly, we can replace our a minus lambda I by 2 minus lambda, 3, 12, 2 minus lambda, as before. Here we are assuming our eigenvector v is equal to a column vector z1, z2. Since we have two different values for lambda, we are going to discuss each case separately. Firstly, we assume our lambda equals 8, so that we can replace lambda by 8. After the replacement, our a minus lambda I becomes negative 6, 3, 12, negative 6. In order to solve this equation, we have to perform the matrix algebra. So if we look at the first row, negative 6, 3, multiplied with z1, z2, we will get negative 6, z1 plus 3, z2 equals 0. Similarly, if we look at the second row, 12, negative 6, multiplied with z1, z2, we will get 12z1 minus 6z2 equals 0. If we try to observe these two equations, we will find that these two equations are actually the same, because if you multiply the first equation by negative 2, you will get the second equation. Therefore, instead of considering two equations, we can remove one of them. Let's say we focus on the first equation. This is the technical part. So actually we have only one single equation, but we have two unknowns, z1 and z2. The correct way to do this is to use the parameter or free variable. So here you can pick either z1 or z2 to be the parameter or the free variable. Let's say we set our z1 to be s, which is the parameter. Using z1 equals s and go back to the equation negative 6z1 plus 3z2 equals 0, replace z1 by s, you should be able to solve for z2. And our z2 should be equal to 2s based on the equation. So in the end, we got our z1 equals s and z2 equals 2s. If you remember, in the beginning, we set our eigenvector v to be equal to z1, z2. Here, we are going to replace z1 by s and z2 by 2s as what we got. Finally, we just factor s out, and the remaining 1, 2 vector will be our first eigenvector, v1. So here we will record our result as the first eigenvalue, lambda 1 equals 8, and the first eigenvector, v1 equals 1, 2. Let me address 2 points here. The first point is that there is actually a correspondence between lambda and v. So for example, in our case, if lambda equals 8, our v is equal to 1, 2. And you can expect that when your lambda equals negative 4, your v will be different. The second point is that I was actually cheating a little bit. So the reason we got our v1 to be equal to 1, 2 is because we set our parameter s to be equal to 1. So you can see that when s equals 1, our eigenvector v is equal to 1 times 1, 2, which is 1, 2. Similarly, if you want, you can set s to be 2, and your eigenvector v will be 2 times 1, 2, which is equal to 2, 4. Both eigenvectors are acceptable, but you only have to record one of them. Basically, s can be any real number, but s cannot be 0. So let's say we just record our original eigenvector v1 equals 1, 2 in this case. Notice that here we only calculate the eigenvector corresponding to lambda equals 8. I suggest you pause the video here and try to use the same analysis to calculate the eigenvector corresponding to lambda equals -4. I will post my solution later, but you should be aware that your solution might differ from my solution by a multiple because you have the freedom to choose your eigenvector. Thank you for your watching. I hope you enjoyed this video.